All right, this is lesson 1.2 for Integrated Math 1, Inequalities and Solutions to Equations. Our con skills are solving equations and inequalities, and this is the 6th and 8th skill in Khan Academy. We have two objectives. Our first one is about inequalities. You should be able to identify and use inequalities. Our second skill is about equations. We talked about equations in the last video, but in this lesson you will be able to tell if an equation has one solution, but you may or may not have known this already. Some equations have infinitely many solutions, and some equations have no solutions at all. We'll get more into that in a little bit, but first let's talk about inequalities. When I was in school, my teachers used the alligator analogy, like the alligator eats the bigger number. Sometimes it was the Pac-Man or whatever animal you want to use. More recently, I have two young boys who really like the show Number Blocks. I know it's geared for younger kids, but the Number Blocks actually has a lot of cool math. I am definitely a fan. So if you've ever seen Number Blocks, or even if you haven't, look it up. And they have a character called Blockzilla. That's pretty cool. But anyways, this symbol here is less than. You could also have greater than. And if there's a line underneath it, that means less than or equal to, or that one would mean greater than or equal to. The reason they're called that is because we read from left to right. So let's do example 1 together. We're comparing 45 and 23, and we would put greater than, right? Because 45 is greater than 23. One thing to note here is that this inequality means the same thing as, we can make it a less than statement if we wanted to. We just change the numbers. 23 is less than 45. Those two inequalities communicate the same exact thing. Let's try example 2. 75 or 79, and we're comparing it to 75. 79 is definitely greater than 75, right? Okay. Go ahead and pause the video. I want you to try to fill in problems 1 through 4. All of these end up being greater than. 57 is bigger than or greater than 13. 42 is bigger than 35. 60 is bigger than 50 or greater than 50. And 320 is greater than 316. But just like I said in the first example, all of those inequalities, even though they all say greater than, we could rewrite it if we flip the numbers around into a less than statement. All right. Let's talk about graphing inequalities. So when we have one variable in an inequality, we graph it on a number line. And we can do that together now. So in example 3 here, I gave you a blank number line. Every time you have to graph an inequality, I want you to put some tick marks on the number line, like this. And whatever we're comparing it to, in this case, we're comparing x to the number 9. Put that somewhere near the middle, and you should have a number or two above and a number or two below. So after 9, 10, 11, 12, something like that. And 8, 7, 6. That's plenty. You really could just have 8, 9, and 10 if you wanted. I don't mind. But we need to graph this inequality now. And if we're going to graph x is greater than or equal to 9, that's what these notes here represent. If there's no or equal to, if it's just less than or just greater than, we make an open circle, and that means we're not including the endpoint. But since this example has a line underneath the greater than symbol, we're talking about greater than or equal to, our graph needs to have a closed circle, which means our solution includes the endpoint. So I'll graph it, say in red. We're going to put a point on the 9, and because x could be equal to 9, we're going to fill that circle in, and then we're either going to draw an arrow from that point to the left or to the right, depending on whether it's less than or greater than. This is saying x is greater than or equal to 9, so x could be 9 or greater than 9. It could be 10, 11, 12, so on. So our arrow is going to point to the right. Okay, and then I'll do the next one in green. So if we're going to graph this inequality, -3 is less than t. We still need to put our tick marks on our number line. So we're comparing t to the number -3. Put that somewhere near the middle. And put a number or two above and a number or two below. This is a little bit different because we're dealing with negative numbers here. So the number that's the next integer that's bigger than -3 would actually be -2, and then -1, and then 0, right? And then we get to positive numbers after. But you don't have to put all of that. I just drew that to remind you about negative numbers on a number line. And then the next smaller number after, lower than -3 would be -4, and then -5, and so on. Now that we have our tick marks, we can graph our inequality. And I should point out that in example 3, I drew the point and the arrow on the number line. If you don't like to do that, there's another way. You could also graph it a little bit above the number line. I don't care which one you do as long as I can see it. So I'll do the other way in example 4, and you just pick whichever way is better for you. So our endpoint is -3. Notice that the inequality is just strictly less than. It does not have the line underneath it, so it's not or equal to, it's just strictly less than. So we're going to leave an open circle instead of filling in that green circle there. And since it says -3 is less than t, we need to think about which numbers could t be. That means t is actually going to be greater than -3, so we'll be pointing to the right. Now, some people have asked me in the past, well, hey, it says less than. Why don't I draw the arrow to the left? Well, that's because the variable's on the other side compared to example 3. So if you like to use that, hey, less than points to the left and greater than points to the right, that's only true when the variable is on the left side. So if you want to actually take this and rewrite it with t on the left side, t would have to be greater than -3, and that kind of follows that rule then. Okay. Pause the video, try problems 5 and 6. Check your work here. Notice that in problem 5, it's x is less than -4. There's no or equal to, so our circle is open. And the numbers that are less than -4 would be -5, -6, and so on. In problem 6, we have a greater than or equal to symbol. So our point is closed, our circle is closed. And the numbers that would fit in for p here, we could say 6 is greater than numbers that are smaller than 6, right? So 5, 4, 3, any of those numbers would make the inequality true. And again, real quickly, remember that inequality means the same thing as p is less than or equal to 6. So if you like using that less than shade to the left rule, that only works when our variable p is on the left side. Okay. Before we solve inequalities, there are some notes that I want you to write with me. You have a blank page in your notebook on page 14. So go ahead and write this here so you have it for your reference later. And then flip in your notebook to page 14. We're on page 11 right now. There we go. Okay. So we talked about equations yesterday where you do the same thing to both sides. But I have a question for you. Can we do the same thing to both sides when we're dealing with inequalities? And the answer is not always, but usually yes. So I have some facts that I'm going to tell you. I'm not going to prove them, but I'll give you a few examples, and hopefully that convinces you. You can take my word for it. I'm not going to lie to you. So the first thing you should know is that we can add or subtract the same number to both sides of an inequality. So I have an example for you here. Here's an inequality. 5 is less than 8. We should all be able to agree on that, right? 5 is definitely less than 8. But let's just try it out. Let's add the same number to both sides and see if we get a true inequality. So since we're not sure yet, I put a question mark there. That's kind of my notation for, hey, I know 5 is less than 8, but I'm not sure yet if I can add the same thing to both sides. So I put a question mark above that less than. So I'm just asking, is 5 plus 10 really going to be less than 8 plus 10? And well, 5 plus 10 is 15. 8 plus 10 is 18. And hopefully you agree with me that 15 is definitely less than 18, right? Let's change the color on that real quick. And I drew my picture here. If you remember the picture from the last video where we want to keep the equation balanced, keep the scale balanced, inequalities are not that way. They're not equal, right? So we're saying that 18 is the heavier number. 15 is less than 18. So if it were on a scale, this side would be heavier and it would push that side down and 15 would go up, right? And the scale stays balanced with our original 5 is less than 8, right? I've got another example here. So again, starting out with something we know to be true, 5 is definitely less than 8, but is 5 minus 10 still less than 8 minus 10? And it is. Again, I'll color code it for you. So if we subtract 10 from both sides of that inequality, we get a true statement. Negative 5 is definitely less than negative 2. That might seem weird to you if you're not comfortable with negative numbers yet, but this is saying that negative 5 is further to the left on the number line than negative 2 is, and that is true. So, oops. So the scale still stays in the same position. It's still tilted down towards the right because negative 2 is the larger number compared to negative 5. All right, so the big takeaway from this is yes, you can add or subtract the same thing to both sides when you have an inequality, just like you do when there's an equal sign instead. Another takeaway is that you can multiply or divide both sides of an inequality as long as it's a positive number. That is really important. I wrote it in all caps for a reason. Here's an example. We definitely know that 6 is a smaller number than 24. 6 is less than 24. And if you multiply both sides by 2, or any positive number really, notice that 2 is positive, we're left with an inequality that is still true because 12 is indeed less than 48. You can also divide by a positive number. Notice that 3 is positive. So we know 6 is less than 24. If we divide both sides by a positive 3, we still get a true statement. 2 is definitely less than 8, right? So the second takeaway is you can multiply or divide both sides by the same thing as long as it's a positive number. But the big difference, this is not the same thing with equations like we did in the last video. We cannot multiply or divide both sides of an inequality by a negative number. That's going to mess things up. And here's the reason why. Again, this is not a proof, but here's an example of why we run into a problem. It is true that 4 is less than 6, right? But if we multiply both sides of that inequality by -3, well, -3 times 4 is -12, and -3 times 6 is -18. But hopefully you notice that -12, that's not less than -18. Remember, on a number line, we have the zeros over here. -12 is actually greater than -18. I skipped a few numbers, but -12 is not less than -18, right? Same thing if we divide. We take a true statement like 4 is less than 6, but if you divide by -2, 4 divided by -2 is -2. 6 divided by -2 is -3. And notice that -2 is not less than -3. This inequality can't just stay here when you divide by a negative. And if you're more visual, this one's easier to draw on a number line without skipping numbers. Say I have 0, -1, -2, -3. Notice that -2 is actually greater than -3. So, again, this isn't a proof, but take my word for it. Write this rule in your notes. If we multiply or divide both sides of an inequality by a negative number, then the direction of the inequality must change. So, for example, if we had 4 is less than 6, we can multiply both sides by -3, as long as we change the direction of the inequality. So if it was less than, we're going to switch it to greater than. And then we get a true statement in the end. -12 is actually greater than -18. Take a moment to write that down, and then we're going to use that back on page 11. The big takeaway from this page of notes we just did is that you can do the same thing to both sides usually. You can add, you can subtract any number you want to both sides of an inequality. You can even multiply or divide as long as it's a positive number to both sides of the inequality. But as soon as you multiply by a negative, you can still do it as long as you change the direction of the inequality. All right. Let's use that result back in the top of page 11. Okay. So we have -5 is greater than 10. Or, I'm sorry, -5x is greater than 10. So -5x is on the left side, 10 is on the right side. Let's divide both sides by -5. Now, we can do that. We can divide both sides of this inequality by -5. But because we're dividing by a negative number, our inequality isn't going to be greater than anymore. We're going to switch the direction. And that's all there is to it. Now we just simplify both sides of the inequality, just like we did in the last video with equations. So we have a fraction on the left side here. -5 divided by -5. That's just a big fat 1, right? Anything divided by itself is 1. And 1 times x is just x. On the right side, 10 divided by -5. Well, a positive divided by a negative is going to be negative. And 10 divided by 5 is 2. So negative 2. And we could graph that just like we did in the notes above if we needed to. All right, let's try example 6. So we're going to take the left side of this inequality, just a 3, and we'll take the right side, negative 5n minus 7. And if it were an equation, if 3 were to equal negative 5n minus 7, we would, according to the notes in the last video, we'd want to add first. Let's add 7 to both sides. In fact, let me move this a little bit. There we go. So I can add 7 to both sides of this inequality, and adding or subtracting does not change the direction. It's still going to be less than. And we can simplify this. 3 plus 7 is 10. Negative 5n doesn't have any like terms on the right side, but negative 7 plus 7, that's 0. That's what we want. We're trying to get n by itself, right? Now we want to get n by itself, so let's divide by negative 5. We divided by a negative sign, or negative number, so the sign of the inequality has to change. It switches from less than to greater than. And then we're going to take this and simplify it one more time. 10 divided by negative 5 is negative 2. That's greater than, remember this is a big fat 1. 1 times n is just n. So negative 2 is greater than n. If you really want to, if you like the variable on the left, you can switch it. You can say n is less than negative 2. Either one of these works. You don't have to put both. All right, so try problem 7 and 8. Pause the video. Okay, so go ahead and check your answers. Problem 7 here. Just like in the last video, distribute first. It makes your life easier. So negative 6 times 4x is negative 24x. Negative 6 times 6 is negative 36. Combine your like terms. Negative 3 minus 36 is negative 39. And then we're trying to solve for x. We don't want that negative 39 there or minus 39. So we add 39 to both sides. And when we combine our like terms, we just get negative 24x on the left, negative 72 on the right, because negative 111 plus 39 is negative 72. Now, we want to get x by itself, so we need to divide by negative 24. We're dividing by a negative, so the direction of the inequality changes. Instead of greater than or equal to, it becomes less than or equal to. And we get x is less than 3. Check your work on problem 8 as well. It's very similar. I'll zoom in. We need to distribute, and then subtract to get the term with the variable on one side and the term without a variable on the other side. And then we divide. Dividing by a negative changes the direction, and we get our solution. All right. Now we're going to talk about solutions to equations. So remember, we had 2 objectives. We just talked about identifying and using inequalities. Now we're going to go back to equations, and we're going to talk about when there's one solution, infinitely many solutions, or no solution. All right, so that blank should say infinitely many. We have infinitely many solutions if this scenario occurs. If the variables cancel out and both sides are equal to each other. In other words, the variables cancel out, and we get a true statement. Okay, so let's say we're solving this equation just like we did in the last video, solving equations. We're going to distribute first. Distribute that negative 4 to v and to 3. Then we're going to add 12 to both sides, combine our like terms, divide both sides by -4, and this time it's an equation, so it can't really change directions. You are allowed to divide by anything you want in an equation, as long as it's by both sides. Now we get something called, different though, compared to the last video. We get -4v is equal to -4v. Something's equal to itself. Well, isn't that always going to be true? Isn't something always equal to itself? You might even notice it here and say, oh, well, then there's going to be infinitely many solutions. But if you didn't, that's okay. We can add 4v to both sides and we'll get 0 equals 0. Well, remember, we're trying to solve for the variable. We're trying to find out, well, what value of v would make this equation true? Well, v can be whatever we want. 0 is always going to equal 0, right? That's always true. So no matter what value you pick for v, 0 is 0. And that means there's infinitely many solutions. Here's another example. Say that I ask you to solve this equation. We'll distribute the 5 to both terms in the parentheses. Combine your like terms. Again, as you get more practice with this, you might notice here that, hey, both sides of this equation are exactly the same. You can stop there and say, well, that means there's infinitely many solutions. But you can always try to keep going, try solving for n. You'll end up getting that it doesn't always have to be 0 equals 0. You might get 3 equals 3 or 5 equals 5 or something. But if you get an equation that it just says that both sides are equal to each other, that means there's infinitely many solutions to the equation. All right. Another thing that could happen when solving equations is that you could get one solution. This case is what you saw in all of the problems in the last video, in 1.1. When solving an equation, there might be a unique solution. So here's an example. We're going to distribute the 7 to both terms in the parentheses. We can subtract 14 so that, we're trying to get the constant terms on one side. In this case, in this case, they both have a 14, right? So the constant term disappears on both sides. That doesn't always happen, but we end up getting 35v equals 3v. And if we subtract 3v from both sides, we'll get 32v equals 0. And we can divide both sides by 32. That's allowed. And 0 divided by 32, 0 divided by any number that's not 0 is still 0, right? So v is 0. I'll try it again here. Here's another example where we will get a unique solution. Again, distribute right away. That is going to save so much headache. We can subtract 18 from both sides. And in this case, the constant term doesn't cancel out, but we have a constant just on the left and there's no constant on the right. So that's good. We're going to subtract 8x from both sides of the equation so that our constant term will be on the left and our term with a variable, our term with x, will be on the right. Now all we have to do is divide by 4, and we get a solution for x. In this case, x is 5. Both of these problems fall under this category where there's one unique solution. Finally, sometimes you get an equation where there's no solution at all. It'll be similar to the first case where there's many solutions, but the variable will disappear and you'll get a false statement. So remember up here I said you'll get a true statement. You'll end up getting a false statement here. Oh. So for example, let's say we're solving this equation here in example 5. If we distribute, we can add 7p to both sides. That way the p term cancels out on the left and we'll just get a Uh-oh. The p term is going to cancel out on the right as well. And we get the statement 36 is equal to 35. There's no more variables, they cancel it out. But this statement is never true. 36 is not equal to 35. So you can just write a line through that. That means does not equal. There's no value of p that would make that true, so we say no solution. Same thing for number 6. So if we distribute, add 2v to both sides, and again, the term with a variable v cancels out on both sides, but we end up with a statement that's not true. There's no value for v that could make 4 equal -3. So we write no solution, and that's it. We have an application problem at the end here, and I want to elaborate on our word problem strategy. Every time you have a word problem, I will give you partial points if you at least do our strategy. Circle the question. So honestly, you should just read through it without writing once. So if we're reading through it, Brett has $30, a $30 online gift voucher. He plans to buy as many books as he can. The cost of each book is $4. There is also a single shipping charge of $2. How many books can he afford without spending more than his gift voucher amount? So we read through it once. The first thing we do in our strategy is circle the question. What do we need to find? And I've already circled it for you. We need to find how many books can Brett afford. Okay? Then we need to underline the important information. It's important that we need to know that he has $30 if we're talking about what can he afford, right? We also need to know that each book costs $4 and that there's a single shipping charge of $2. After that, because this is a solve an equation type problem, we have a variable, we're going to define it, and then we'll solve for it. So this is huge. If you circle the question, underline the important information, that's worth some credit. And then if you can say, hey, let X, or you could say B for books, whatever variable you want, just define it and say it represents the number of books that Brett buys. And then I think that the trickiest part is this last part. We need to set up an inequality, but words are okay at first. You don't have to jump from defining your variable to straight to an inequality. You can say, well, okay, the money that Brett spends, he has a cap. He can only spend the $30 that he has, right, in gift vouchers. So the money he spends needs to be less than or equal to that amount. He could spend $29, he could spend $28, but he can't spend $31, right? He could spend all $30 if that's possible. We don't know yet. And then slowly we want to work towards turning these words into expressions, or expressions. So the money he spends, how could we write that in numbers and variables and stuff like that? Well, that's what we underlined. So, I guess not that one, but the cost of each book is $4. So if he buys X books, we would need to multiply that by 4 to see how many dollars that's worth, right? If he buys one book, it's $4. 4 times 1. If he buys 2 books, it's going to be $8, right? Because it's 4 times 2. Or if he buys 10 books, it would be $40. That's too much, but we get that because it's 4 times 10, right? So 4x is the expression that represents the cost of the books. But don't forget, we also underlined another piece of information. There is a single shipping charge of $2. So he's going to have to pay 4 times the number of books that he buys plus $2 in shipping. That's our inequality that we're trying to solve. If you can get this, that's the word problem part. And then it's just like the examples we've already done, right? So you can subtract, you take our inequality, you can subtract 2 from both sides. We'll get 4x is less than 28. And then if we divide both sides by 4, we get our solution. X is less than or equal to 7. However, our last step in this word problem strategy, remember the question that we circled? We need to answer it. Don't just answer it in symbols. Even if you get here, that's great, but write a sentence. You were given a word problem, a sentence, a question. So make a statement answering the question. Answer the question in context. That's huge. So to get 100% credit to do your whole word problem, you should answer something like this. It doesn't have to be the exact words that I did, but you should say that Brett can afford up to 7 books.